Welcome back class to our course on mechanical behavior of materials part 2. So in the last class, we started talking about fracture mechanisms, especially for metals and alloys. We discussed about how to classify fracture, and then we started talking about ductile fractures in metals and alloys. Okay. So when we have pure metal, then you are going to see rupture. And if it is metal, commercial metal and alloy, then we are going to see cup and cone fracture. Okay. So now we'll continue with the ductile fracture behavior of commercial metals and alloy. Okay. So we'll talk about ductile fracture. Okay. So what I have shown here is SEM micrograph of 7075 aluminum alloys. So this is age hardenable aluminum alloy where zinc, magnesium and copper are present as major alloying elements. In addition to obviously aluminum as the main element. Okay, what you see here are second phase particles. So if you remember, we discussed in the last class in very brief about the presence of second phase particles or inclusions, which are responsible for void nucleation. Okay, so I just wanted to show you those particles here. So what you see, all these are second phase particles, and this gray one is your matrix. Okay, and the circle ones, all these are second phase particles or inclusions. Okay, so depending upon the type of materials, you can have different type of second phase particles. Okay, and so let me just summarize very quickly of different second phase particles in several materials. So you are going to see inclusions. In some books, you will see these are also called second phase particles. They are found in commercial metals and alloys. Okay, as I have shown here. So aluminum 7075 is a commercial alloy, right? Remember, if it is pure metal, then you're not going to see all these inclusions. Okay, and that's why it doesn't show you cup and cone fracture, it shows you the rupture. But as soon as we have second phase particles, you are going to generate voids. We'll see it how. Okay. So now these inclusions, how do they form? So they are actually coming from either the scrap materials you are using during casting or melting, as well as the ore, right? You are getting all these alloys or metals from extraction, and the initial material is the ore, right? So if you see in aluminum 7075 alloy in this microstructure, all these white second phase particles, they are iron rich inclusions. Okay, so they contain iron. And this black one, these are Mg2Si inclusions. So these are silicon rich inclusions. Okay, so depending upon the type of materials, you are going to have different kind of inclusions in second phase particles, and these are typically intermetallics. Okay, and in aluminum alloys, we have lots of intermetallics. Okay, so they come from traps or odes and typically form during casting. Okay. And if after casting, if you do thermomechanical processing, they are going to break down. Okay, but typically they form during casting. Now, if you talk about steels, you are going to add carbide formers, nitride formers, or carbonitride formers. Right? Those are also second phase particles, but they are actually providing strengthening. Remember these inclusions, what I just mentioned, they are very harmful to the materials. Okay. So nitrides, carbides, carbonitrides in steels. And if you talk on steels, you know about MNS inclusions, right? Even alumina, presence of alumina in steel, right? So these inclusion, and if you remember MNS inclusions, they form because you want to get rid of something called hot shortness in steels. So you add Mn and it reacts with sulfur and it forms MNS inclusions. And they are also the sites where the crack nucleates when you load the samples. Okay. So overall, you have the presence of second phase particles in all types of commercial metals and alloys. And typically, under the applied stress, these second phase particles are going to be the initiation sites for void nucleation. Okay. So the overall process, if you talk about the ductile fracture in commercial metal and alloys, it will be so it starts with void nucleation, then void growth. Once it has nucleated, it has to grow, right? So void growth. And the last one is void coalescence. So these are the three processes for ductile fracture in metals and alloys. Commercial. Okay, so we will now talk one by one about all this. So overall, now let me write down a couple of more sentences before we begin. So it starts with void nucleation. Then you have growth of voids due to plastic strain and hydrostatic stress. Okay, and the last one is coalescence of voids with adjacent voids. Okay, that means if I have a material, suppose you are doing tensile test itself, right? So you have a material and then you have some second phase particles, right? I've shown you the image, one of the image microstructure of aluminum alloy where you can see those second phase particles. So suppose you have these second phase particles, right? So what will happen? You are going to generate voids in the second phase particles, right? And they are going to say grow with time with strains. Okay, and finally they are going to merge. So I'm just giving you a rough schematic. Okay, so finally they are going to merge, something like this. Okay, so this is how you are creating voids, then these voids are growing, and finally this leads to the fracture. So this is the overall fracture of the mechanisms. Okay, so now let's talk about first void nucleation. Void nucleation. Okay, so this nucleation has been attributed to two processes. Either of the two processes are going to be there. The first one is particle cracking, and the second one is interfacial debonding. So void in a given material, when it is under applied stress, can form in the particles, right? That much you know. Now there are two processes. Either particles can crack. So if you have this particle, it can crack. Okay, so it can crack. So this will lead to void nucleation. Okay, or crack nucleation there, which will in turn become void. Or second, you have a particle and there is an interface between the particle and the matrix. Okay, see the yellow line. So this is your interface. Okay, so this interface can also break. There might be debonding between the interface of the particle and the matrix, which will lead to the crack nucleation or void nucleation. So either of these two can happen depending upon the strength of the interface. Okay, so if the strength of the interface is higher than the strength of the particle, then obviously interface is going to crack or debond. If the particle strength is lower than the interfacial strength, then the particle is going to crack. Okay, so depending upon the nature of the interface, you have void nucleation. Either of these two processes are going to be active. Okay, so if interface strength is higher than the particle strength, and remember, this is what you also observe during deformation in composites. We'll discuss about that also. Okay. Then interfacial debonding will predominantly occur. Okay. And if interface strength is lower, okay, so just made a mistake. So if interfacial strength is higher, then so let me make it lower. Okay. Now if the interface strength is higher than the particle strength, so particle fracture will occur. Okay. So whatever might be the case, whether it is particle cracking or interfacial debonding, you are going to observe nucleation of crack or void there. right, at the location of these particles. And that is why, I mentioned in the last class the distribution of these particles, volume fraction of these particles, size of these particles become very, very important when you talk about ductile fracturing, commercial metals and alloys. Okay. So there are some models to which give empirical relations depending upon the size of the particle, etc. We'll just talk about that briefly. And these are for void nucleation. Okay. So there are two models. First is the continuum, and the second one is dislocation, particle interaction. And this one is typically valid for less than 1 micron. Okay. So now let's talk about both the models quickly. So the first one is continuum model. This was proposed by Argan et al. And it gives you the critical stress required for debonding to occur. Okay. So interfacial strength at a cylindrical particle. Okay. That will be given as sigma C, sigma bar plus sigma M, where sigma bar is your remote effective von Mises stress. And sigma M is hydrostatic or remote hydrostatic stress. And what is sigma C? It's the interfacial stress, but that to the critical stress where interface is going to debond. Okay, so sigma C is critical, and that's why subscript C is there. Critical stress, okay, or critical combination. Critical combination of both the stresses. So sigma bar and sigma M. And it is equal to interfacial stress for debonding to occur. Okay. So sigma C is the critical stress, a combination of both sigma bar and sigma M, where this stress is reaching to the debonding stress. Okay, where you are going to observe debonding of the interface between the particle and the matrix. Okay, now you see you have sigma M there, which is actually sigma 1 plus sigma 2 plus sigma 3 by 3. So you now are talking about the triaxiality, right? So you have all the stresses there. Okay, so sigma bar, it's one Mises stresses, so it is 1 by root 2 sigma 1 minus sigma 2 square, sigma 1 minus sigma 3 square, and sigma 2 minus sigma 3 square half, and sigma m is your hydrostatic stress. So is sigma 1 plus sigma 2 plus sigma 3 by 3, where sigma 1, sigma 2, sigma 3 are principal stresses. Okay. So if you see, if you have higher amount of sigma m, you are reaching the critical stress earlier, right? So if you have triaxial stresses, you are reaching sigma c earlier. That means you are actually promoting the crack nucleation. Okay, and that's why triaxial stresses, I'd say, little bit dangerous as compared to biaxial stresses. Okay, so increasing sigma m will increase the probability of crack nucleation, right? So this is about the continuum theory. Now we'll talk about dislocation model. So dislocations, since this is a ductile material, you are going to see movement of dislocations, right? And dislocation interactions. So these dislocations are also going to interact with the second phase particles. So you can think of like, dislocations are moving in a slip plane, and then they are seeing the particles, right? It's like then pile up, right? So all the dislocations are going to get pile up as soon as they see these particles, which in turn is going to increase the stress, right, at the leading dislocation, right? That can lead to the void nucleation, right? So let me write down the same thing. So dislocations near the particles can elevate the stress. Okay, so you can think of pile up condition. So it is similar to that. Okay, you just think of the similarity between this and what we have discussed during grain boundary pileup. Now this increase in the stress is given by, let's say, that is sigma d, delta sigma d. So there is an empirical relation, and that is given by 5.4 alpha mu strain Bursar's vector and then R, where alpha value goes from 0.14 to 0.33. Mu is your shear modulus. Okay. Then epsilon 1 is your maximum remote normal strain. B is your Bursar's vector. R, now this is important. R is your particle radius. Okay. So it predicts that if R is smaller, delta D is going to be higher. So smaller the particle size, it becomes more easier for increase the stress. Right? Now again, interfacial stress we can figure out. So inter KCR stress in this case combination of delta sigma D and maximum principal stress. So you have increment of stress because of the dislocation interaction with the particle. That contribution is given by delta sigma D. You are also applying the stress, right? So that contribution will be given by maximum principal stress. So now you have a combination of both the stresses, and that will we need to add these two so that we can obtain the interfacial stress. Now again, there will be a critical combination of these two stresses so that the stress, interfacial stress can reach to the debonding stress. Okay. So at a critical combination of both stresses, critical stress for crack nucleation will be given as sigma C, sigma 1 plus delta sigma D. So you're going to have a combination of sigma 1 and delta sigma D, and at certain point you are going to reach to a critical stress where you are going to see debonding of the interface, and that will lead to the void nucleation. Okay, so that is one way of understanding. The another way is, remember, you have these particles and then you have the matrix. Both are different materials themselves, right? So their properties are also going to be different, and these particles are harder, right, than the matrix. So the strain compatibility issue is going to be there between the particle and the matrix. So matrix is going to have more and more strain accommodation as compared to the particle. So there will be strain incompatibility, and that will lead to the generation of something called GNDs, geometrical necessary dislocations. And this is happening because there is a strain gradient between the particle and the matrix. And why it is happening? Because both the particle and the matrix exhibit different properties. One is harder, another one is softer, and matrix is going to accommodate more strain as compared to the particle, right? So there will be gradient of strain, and that will lead to the generation of GNDs. So that is another way of thinking of the interaction of dislocation with the particle, and this will also lead to generation of stresses at the interface. So matrix is ductile, but particles are predominantly brittle, or say hard, right? See, again, all particles are not brittle. Okay, and that's why I have used predominantly. So we are assuming that the particles are harder than the matrix. Okay, this means that particles are not able to accommodate strains. So most of the strains are going to be accommodated in the matrix. So there will be a strain gradient. Okay, so you are going to have strain incompatibility. between particles and matrix. And this will lead to generation of GNDs, which is geometrically necessary dislocations. Okay. So there is an incompatibility between the matrix and the particle. So there is a strain gradient. And to accommodate that, we are going to have more number of dislocations. And that's why this is also called geometrically necessary dislocations. And these are also going to increase the stress, right? So if you have this particle in the matrix, you are going to have GNDs like this. GNDs. Okay, all caps lock GNDs. Okay, so this is what the void nucleation is about. And now if you see, we have mostly discussed about the interfacial stress. We have not talked about the particle fracture at all. But in reality, if you see in most of the cases, you are going to see particle to fracture rather than interfacial debonding. Again, you remember we have discussed, it depends upon the nature of the or strength of the particle as well as interface, right? So whichever is greater, other is going to fail. Okay, so if the interfacial stress is higher, particle fracture is going to occur. So these two models are mostly dealing with the interfacial stress. As soon as the combination of the stresses going to reach the critical stress of the then interface is going to break. They don't talk about the particle fracture. And in fact, if you see the continuum model, it doesn't talk about at all about the size of the particle. At least the other one talks about the size of the particle. Okay, so there are some lacuna in these two models. Let me write down. So experimentally, larger particles are more prone to void nucleation. This has been observed experimentally. But if you see the dislocation particle interaction model, there we saw that if the particle size is smaller, the interfacial strength is going to be higher, right? And then it will lead to earlier void nucleation, right? But experimentally, it has been observed that the larger particles are more prone to void nucleation rather than the smaller one. Okay? Now, continuum model is independent of particle size. And dislocation model predicts that decreasing particle size is beneficial for crack nucleation. That means it becomes easy to nucleate the crack. Okay, easier crack nucleation. Now the third point is that both the models only consider debonding and not particle fracture. So in both the models, we talked about the interfacial stress and they consider only debonding, not the particle fracture. Okay. Then the last one, larger particles are likely to crack since they have high probability of exhibiting cracks. Okay, so if your particle size is larger, there is a high probability or the probability is higher to have Griffith crack there, right? And if you compare, we have discussed the Leonardo da Vinci first experiment. Larger the length of the wire, the more easier or the probability of fracture is higher, right? The strength was going down in Leonardo da Vinci's first experiment. We discussed that in one of the lectures. Okay. So if you have larger particle size, there is a more probability of finding the Griffith crack. And that's what you see experimentally, that larger particles are more prone to void nucleation rather than the smaller particles. Okay. And moreover, after casting, say that aluminum alloy microstructure I showed you. So after casting, you are going to roll it, right? Or extrude it. You're going to do some forming processes. During those forming processes, because of the applied stress, these particles are also going to crack. So there can be pre-existing crack in these particles, right? So it becomes much easier to fracture the particle when you have pre-existing crack. So if the particle size is larger, there is more probability of finding crack. So experimentally, we have observed that void nucleation occurs in larger particle size. Okay. Now let's talk about growth. So we have discussed about the nucleation of the crack. Now these void, and now these voids are going to grow, and finally they are going to combine or coalesce. So void growth and coalesce. So after void has formed, they grow and coalesces with further plastic strain and hydrostatic stress. Okay, so you have nucleated the void. Now under the applied stress, that too, the probability is higher, or I would say it is more prone to void nucleation and growth when you have triaxial stresses. Okay, so they are going to grow and finally they are going to merge. So if the volume fraction of particles is less, each void, whatever has been nucleated, okay, either by debonding or the fracture, since the volume fraction is less, they are going to grow independently. Okay, that too in the initial phase. And with further grow, voids are going to interact. And they are going to link. So linkage. And when this happens, there is a localized plastic deformation. I will show you the schematic so that you can understand it better. So plastic strain is concentrated along a sheet of voids and local necking instability develop. Okay, and these two here will come under coalescence. Okay, so once you have formed the void, they are going to grow, right? So if the volume percentage is small, obviously, right, then they are going to grow independently because the volume fraction of the voids or volume fraction of the particles, because the voids are going to nucleate at the particles. Right? Now, if the volume fraction is large, there will be interaction from the beginning, right? Even if the volume fraction is small, initially they will grow independently, but as they grow, the distance between two voids are going to decrease. So there will be interaction again at the later stage of the growth of voids. And then there will be linkage. They are going to coalesce with each other, and then finally fracture is going to occur. Okay. So there are two mechanisms. One is called internal necking, and another one is void sheet mechanisms. We'll discuss one by one. So first, we will talk about internal necking. So suppose you have a sample. So we are not talking about internal necking. So you have a sample. Okay? And then you have lots of particles. Certain phase particles are like this. Okay. Now voids are going to nucleate in these particles. So you see voids. So I have drawn, three voids. You can get multiples. So let me draw multiples. So void nucleation at the location of particles. So either debonding or the fracture of the particles, whatever might be the case, you have nucleated the void, right? If now they will grow. So if you see, now let me magnify this region here. Let's see, I am talking about now these two particles. Okay, and let me magnify these. So I have this particle, and then there is a void. Okay, I have another particle, and then there is a void. Right now, there is no void between these two particles. Right now, can I assume that there is a necking here? So there is a neck. So these two are like neck to me. Okay. So a strain is going to localize now between these two regions. because of the formation of neck. And remember, this neck is, if you correlate this neck with the notch, there is a stress concentration, right, between the neck region. And that is what you also observe during uniaxial tensile loading. So as soon as there is a neck formation, it acts like a notch if you just correlate. So there is a stress concentration, and near the stress concentration, because of the stress concentration, you have triaxiality, right? And that's what you see during tensile loading, that after neck forms, you cannot have uniaxial tensile relations in the neck region. Okay. So for all practical purpose, we can assume that there is a neck here, right? Now there is no particle. So we can also assume that this region is pure. It is acting like a pure metal. Okay, right? Now think about it. This region is acting like a pure metal. There is a neck formation. Can we now say that this is going to rupture? Right? During tensile loading, after neck forms, pure metals are going to rupture, right? So what we can draw now, we can make a schematic like this, that you have a particle. I will now magnify it. Okay. You have another particle, and you have these two voids here. Okay. Now there is a local necking, right? Local necking, and finally it is going to rupture because it is acting like a pure metal. Okay, so you are going to see something like this. Right. So if you remember during tensile loading of pure element or pure metal, it was like this, right? So I'm doing the same thing. So this region here at the center is acting like a pure metal. So I'm just making it two lines like rupture. Okay. So overall, I can write that material between voids are now pure. Okay, so there is no particle. So you can have acting as microtensile sample. Okay, that too of pure metal. So you are going to have necking and finally rupture, which is like pure metal. Okay, so you are going to have a structure like this. Okay, and this is very well valid when you have single population of particles. That means uniform sized particle. So particle size, the second phase particle size are uniform, almost uniform, right? And they are going to generate these voids. The region between the voids, they are going to act like the pure metal microtensile sample. They are going to neck, leading to the rupture. Okay, so you are going to obtain finally uniform sized dimples. Okay, so now I'm introducing a term called dimple. So now let me draw for many voids like this. So you have a particles like this, and they have generated these voids. Okay, now So you are going to have strain localization here between these regions. So I'm showing you how this forms, the dimples forms. That is what I am now showing using schematic, rough schematic. So now what will happen? You are going to see the growth, and since neck has formed. This is how it is going to. Finally, it will rupture. So I'm just giving you the schematic in between what is happening. This neck region is going to grow, right? And remember, these are voids. And the dots here, these are particles, second phase particles. And finally, what is going to happen is the merging of all these voids. So here you have necking and then growth also. Right? So if you now merge these voids in the second diagram, okay, so now these are going to merge like rupture and so on in this side also. Right? So finally you are going to end up getting a structure like this. And so on. Okay. So these are your voids. And the structure, what you see, now if you open these parts, right? Now there are two parts, right? So this is the line where your fracture is occurring of the sample, right? So now you got two parts. If you see these two parts from the top view, you are going to see voids, right? So these are the voids here. Big voids. Okay. On both the sides of the sample. So if I now just see from the top view or say side view of the sample after fracture, you are going to see these voids, right? And these are called dimples. Okay, so these are your dimples. Right? Now what happens to the particle? So if you remember in the first diagram, we have particles here, right? These dots. So in the second one also, you're going to have particle. So now this particle can sit either on this side or on this side, right? So if you just see both the surfaces of the fracture surfaces, you are going to see particles inside those dimples. They are sitting either on one side of the fracture surface or other side of the fracture surface. The particles will be there. It has to be there because the nucleation of the voids has occurred in the particle or at the location of the particle. So particles will be present in almost all the dimples. Okay, either of these two sites, if you observe in ACM, you will be clearly able to see those particles. These particles can be small or larger, right? But those will be there. Okay, and both sides you are going to see dimples because of this. Okay, so I hope you have understood how dimples are forming. So if you see here, these are uniform size dimples. Why? Because the particle size is uniform. They are going to nucleate. They are going to grow together. So you are going to see dimples of almost uniform size. So if you see now from the top surface or top side of the fracture surface, you are going to see dimples. And inside those dimples, you are going to see particles. Okay, so these are your second phase particles, and this is your dimple. Now in three of the dimples I have not drawn. So if you see the other side of the surface, fracture surface, okay. So let me mark this 1 and 2. There are two sides of the fracture surface. Okay. So I'm seeing now top view of the fracture surface 1 like this. Okay. So you see dimple and then you see void particles there. So these three particles which are missing in these three dimples, if you see the second surface, you will see the particles. Okay, so you have to just see both the surfaces to understand it. So particles can either fracture or debond. If it is fracturing, then one per side of the particle will be on one side, another part of the particle will be on the other side. If it is debonding, the whole particle will be either on the first side or on the second side of the fracture surface. Okay, so this is because of the uniform size. The second one was where you have non-uniform distribution of particles. Okay, which is void sheet mechanism. So you have multi-model distribution of particles. So instead of a single population, single size, now you have distribution of the size, different size. Okay. So let's say aluminum alloy, you have larger particle size, which are inclusions. Then you can have dispersoids, you can have precipitates. So you have different size of second phases present in alloys. Okay. So typically, as we have discussed, the void is going to nucleate first at the location of larger particles, right? So voids nucleate at large particles first. Okay. Now, once the voids have nucleated at the larger particle, there will be strain localization nearby that region, right? Because of the stress concentration. So what will happen if you have smaller particles there which were not fracturing or which were not attributing towards the void nucleation before, now because of the strain localization, they can also take part in void nucleation. Correct? So the void will now further nucleate in those small particles which are distributed around the large particle. So now growth of these voids which were nucleated at the location of large particle occurred due to strain localization. Okay, between voids. Now, because of the strain localization, secondary voids are going to form. Secondary voids nucleate between these primary voids. So let me call these are primary. Okay. Primary voids. So what is happening? Smaller, more strongly bonded particle which require higher strains for void nucleation. Now they can nucleate, can now nucleate voids. Okay, and these are actually secondary voids. Okay, and typically these secondary voids are in narrow bands or say sheets called as shear bands. Okay, now let me draw a schematic so that you can understand it better. So you have distribution of particles. So suppose you have two big particles like this. So these are large particles. Okay, so void is going to now nucleate in these large particles first. And they are going to grow independently because of, say, the distance is larger. If distance is smaller, then they are going to interact with each other, right? And now there is a strain localization between this region, right? In this region here, because of stress concentration, right? So now what will happen? Now suppose you have smaller particles, a distribution, like something like this. Okay, so now because of the strain localization, you can nucleate voids. So previously these particles were not contributing towards void nucleation, right? Now because of the strain localization, because of the formation of voids in the larger particles, now you can nucleate voids in the smaller particles. And again there is strain localization because of these small voids, so you can create more number of voids, right? Now all these voids are going to grow and interact, and finally you are going to have a situation like this where you have these particles, and then remember that concept of pure metal between these is going to be valid between the smaller particles as well as smaller and larger particle, right? So they are going to rupture. That is very nice for understanding, right? Just assume that there is a micro tensile sample in all these regions. On the left side now I am drawing. And these are like, there are no particles, so they are pure, so they are going to rupture, right? So your final schematic is this, and it is going to now fail along this direction, right? So this is like your fracture plane. So you are going to again get the two fracture surfaces with lots of dimples. So these are your dimples now. These are your dimples on the both fracture surfaces. Okay. Now there are two sides of dimples here. I'm assuming that they are by distribution of a bimodal distribution of particle size. Okay. So this one is larger dimple, and these are your smaller dimple. So smaller particles are related with the smaller one because they are very near. So as soon as they grow, they coalesce, right? So they don't have much space to grow. Okay, and then you have larger dimple because of the growth. Okay, so now you see bimodal distribution of dimples. Okay, because we have bimodal distribution of particles. If you have multimodal distribution of particles, then the dimple size is going to be completely non-uniform in the fracture surface. Okay, because particle size are different, distribution is going to be different in different directions. So as soon as voids grow, they are going to coalesce. So obviously dimple size is going to be different, right? So this is all about void seed mechanism and internal necking. Okay, so we have discussed about the void nucleation and growth, as well as void coalescence and the dimple. So let me show you quickly one SEM image of dimple. Okay, so this is a fracture surface, one side, okay, of some alloy, and what you see here, all this. So these are your dimples, right? You will see the same thing on the other side of the sample. So these are large dimples. Now you see smaller dimples also. You can see clearly, right? All these are smaller dimples. Okay. Now there is medium also. Okay. So this surface is full of dimples, right? And I would say that this is multimodal distribution of dimples. Okay. So now we'll close this class and then we'll meet next week. Thank you.